So today we're going to have a bit of a discussion about offline power factor testing because that is one that I found to be a little bit on the puzzling side for a lot of folks, myself included, when I because that's really what I started out with in substations many years ago now, and I moved into that work maybe 2 or 3 years into my career and began operating test equipment in the diagnostic group. Uh, and it was I did that for a number of years. I really enjoyed it. It was a lot of fun. But I found out after I'd been doing it for 2 or 3 years that I didn't even have a basic concept of what I was doing. So that motivated me a bit. I had learned a little bit about power factor, I guess, right after I'd started going to school at night, and I took an AC class, and we covered it in that AC class. But as far as formal training in power factor, I really had not ever had any when I went to work in that group. So when I moved into management, we started doing some sessions. I was trying to put something together that I thought would, operating the test equipment takes some training, all right, but you can learn how to operate diagnostic test equipment and really not really know what you're actually doing. So you theoretically you could learn how to operate it. You've got parameters that you go by, and you read your readings and you look and see if everything lines up, right? And the problem a lot of times can lie with the fact that maybe you're performing this test for years and you don't know what questions to really ask. So if you get 4 or 5 years into this, you might even be less prone to admit that you might not understand some things about it. So trying to have some sympathy towards that, because that described me my first couple of years of doing this test. I had numbers, if you look at Doble or Megger, but I think Doble's probably really cornered the market there, although Omicron and Megger make some good offline power factor test equipment as well. But Doble has this massive database, and so Encore, in the form of at least Dallas Power and Light in its original state for that entity, it had been clients of Doble since like the, I don't know, late 50s, early 60s, I guess. And so they had access to that database, which most of you on the call, regardless of what test equipment you do own, you probably have some database there, and there may be some kind of a smart system with it. So I remember when they first started computerizing the power factor test sets, and I thought to myself then, I wasn't real fond of that idea because it automated everything, which is good for streamlining things, but it eliminated this problem that a lot of folks may have had with getting test reports where maybe the numbers where you actually had to run the calculations and write those calculations down. That pencil would sometime slide a little bit, and you might end up with a better reading than you really had. We used to call that pencil whipping. So the automated test sets took care of that, but it did something to the playing field. So I wanted to really put together just a simple way of rolling this out and looking at it. So if you're on the call, you got your electrical engineering degree, you're pretty versed in power factor. This presentation and how it's rolled out, you may go, well, I never really thought about it like that before, and at least I hope that's it. But if you take someone that has basically no electrical engineering background and you're trying to explain power factor to them, and you begin to rattle off some in-depth versions of power factor, you probably lose somebody within about a minute with that explanation. Because folks begin to feel a little bit inadequate because of maybe the lack of electrical theory background. So what you're going to see today is a little bit of a different twist on this. And I've done it several times over the years, although not as much as DGA, but I hope you find this helpful and useful. So first, I wanted to start off with something that, so yesterday or day before, I was talking to my wife, and I was telling her, I said, I think I'm starting to look a little shaggy here. I'll tell you, of all this, not getting out and interacting with the general public, one of the things I really miss is the lady that cuts my hair. All right. So I said something about that out loud. Now, if you've been married more than about a day, you really ought to say things to yourself before you say them out loud. So my wife said something to me. She goes, well, hey, I'll give it a shot. And that reminded me of something. I turned her down, okay, nicely, because she's never cut hair before in her life, and I really didn't want that experiment on me. But it reminded me of something. It reminded me of trigger words, right? So when you hear somebody say, I'll give it a shot, there's not a lot of confidence in that ability to get an end product that everybody's going to be satisfied with. So I think of this in terms of trigger words, and I used to use this when I was at the utility quite a bit with the district and talk about safety. Because early on in my career, very early on, I knew a few folks who used some terms that kind of puzzled me a little bit as it related to safety. So I started thinking about this, and I thought, well, these ought to be words that really trigger me to take a step back. And so if you've been in a substation and you've worked in a substation before, and very many of you on this call have as our customers, you've probably heard these terms before. So, and if you've spent any amount of time at all visiting one of your coworkers in a hospital due to an electrical burn, this should get your attention. So today I kind of wanted to start out with this, and trigger words, that's kind of what I call them. When you hear things like, I think, so, I think it's dead. I think it's been de-energized. That to me is a trigger word. So I need not only for somebody to be absolutely positive about whether or not something's de-energized, I also need them to show me how it was de-energized. Okay, and I'm sure you feel the same way. I believe, that sounds really good, but we all believe a lot of things that aren't true, right? I believed in Santa Claus when I was little. Turns out there's no Santa Claus. So if that disappoints anybody on the call, I'm sorry. I didn't mean to ruin Christmas for you, but we believe a lot of things. Doesn't make them true. So this thing of verifying things is really, really important. And just about every accident I ever did a review on, these words came up. Well, we thought, I didn't add that one to this one, but kind of, I think, right? We thought this was the way it was. We thought this, and it turns out whatever you thought or believed wasn't true, and now somebody's in the hospital. I feel. That's a good one, I feel like if we do this, well, I don't like hearing those words. I really, when you get behind that substation gate, these are words that ought to go out the window and never be used at all. So I kind of wanted to bring that up this morning before we get started, because when you start talking about doing offline testing, there's a misnomer out there that this test equipment that we're using for power factor testing won't kill you. Because it's, and I've heard this term before too, and I don't like this term at all, test voltage. You ever heard that one? Well, it's a test voltage. Does that somehow make it less dangerous in reality? No, it really doesn't make it less dangerous. So the test equipment, all of the protection on that test equipment that we use is designed to protect the equipment, not us. So if you've never really thought about this before, and you consider a 138 kV transformer with a 15 kV secondary, and somebody's climbing on top of that transformer and shorting the transformer out, it's out of service, everything's locked out, it's grounded, disconnected, You go up, you connect your bushings together on the high side, you go over on the low side, you connect those bushings all together because you need to make two big pieces of copper there, right? That's what you need to perform power factor, and we'll get a little deeper into that. But when you do that, when you do that, uh, you while you're up there, you're going to eventually you're going to raise a high voltage lead up, and you're going to put 10 kV on that transformer on the high side, and then you're going to do it on the low side. Well, 10,000 volts is 10,000 volts, and that test circuit's only going to trip when the equipment, the transformer that's likely in somebody's vehicle, when that transformer needs protecting, that's the only time that test set's going to trip. So when it sees more current than it needs to see, it's going to trip. And I can't remember off the top of my head, but I think those circuit breakers on those transformers to perform power factor, I think they're 200 milliamp breakers, but I can't remember. Could be 400. And for those of you on the call that have done any investigating into this, you know that it doesn't take very much. It takes a lot less current than that to kill somebody under the right circumstances. So you just need some good body resistance, good low body resistance. You apply 10 kV to that, and you could find yourself very easily not waking up again. So I've seen this test set blow holes in people's feet before. So if you use terms like test voltage, maybe figure out a new way to say that so that it doesn't make the potential that's being applied sound somehow less troublesome, okay? Because the test equipment we use for this is very dangerous, which is why we have some pretty extreme safety precautions in place these days to operate that test set. I'm not going to, for those of you on the call that don't know what went on in the old days, and by the old days I meant sometime prior to the 90s, let's say, I will not share with you how we did power factor testing back then because it would probably give you a heart attack. But anyway, so today I want to talk a little bit about kind of what it is in its simplest form. And we're just trying to communicate a message here, right? So don't get overly tied up in, well, that's not how I heard about power factor. We're just trying to roll this out in a way that it says, if I'm in an office, let's say, and I'm supporting the field. So if you're managing operations or you're in operations, then the things we're going to talk about today, you may even know a lot of these things. And I just want to encourage everybody to go on mute again. You're supporting that function. So you're in an office, you're looking at dissolved gas analysis, you're looking, you understand enough about power factor, maybe you're even reviewing the results, but you're not actually engaged in the outage, or you're not engaged in the maintenance activity of that, but you do get the results, and you do review the results, those kinds of things. Then maybe this will be a little helpful, and I think it's going to be helpful either way. Or maybe you don't have anything to do with power factor at all, but you know a lot of the folks you're tied to in your utility, they do this test, and you just want to know a little bit more about it. So to tell on myself a little bit, so early on I had gotten into this diagnostic group in my career. This was many years ago. And because I find it hard to believe it. I think I've been in this business now I went in 1977. So what is that, 42, 43 years ago? I remember when I was 43. So I've been doing this a little while. But I have, and I've said this nearly in every one of these little seminars that we've done. Look, if you can find a way to simplify the communication basics of all of these various things that we do. There are folks that need to know power factor inside and out, okay? And then there are those folks that need to have a general knowledge of the concepts of power factor. Just like there are folks that need to know DGA inside and out, dissolved gas analysis. And then there's those that just need a quick review on these things, right? So just kind of a little insight into it. So it really depends on what your role is. But for those of you that don't perform this test and really haven't performed it or not real sure about it and what it is and what the crews are doing, you'll find this rather valuable to you. For those of you that do it every day, hopefully you'll pull something out of here. Why is it a great tool for substation asset testing? So we'll visit with that a little bit. And that's pretty simplified concepts here that we're going to deal with. And then responding to results. So early on when I was doing this test, it takes a little while to learn how to operate the test equipment. And so once you get through that and you get pretty good at operating the test equipment, along the way, sometimes folks forget to ask exactly what it is that's going on with that test. Maybe they ask it early on, but the answer was so far over their heads that they got lost in that translation, learned how to operate the equipment, and never quite got back to the whys of this. So today what we're going to do is just maybe discuss it from that standpoint. So it's just a form of AC testing. It applies voltage, measures a leakage or a loss of current of electrical insulation in the form of watts current. Power factor is very voltage dependent, so we'll talk about that a little bit. It's a test run to evaluate the integrity of the electrical insulation. So if you ask any diagnostic person on the planet that's doing this test, what is power factor? They'll normally use that last sentence. That's the one I used because I at least knew that what I was doing was going to tell me something about the insulation. I didn't really understand the number that I was obtaining. I didn't necessarily know what that number represented. I only knew, hey, I should be at about 0.5%. I'm at 2%. There's a problem here, big problem. But if somebody asked me what it was, that was my standard answer. It's a test used. You know, we check the integrity of the insulation on this electrical equipment. But if they pinned me down any further than that, I was probably going to sink. So I did get pinned down one night. Now, if you promise not to tell anybody, I'll tell you this story, okay? So don't share this with anybody. This is a secret. So I was at a downtown building. I was very young. I was probably 20, 21 years old. I had just started going to school at night. And we were testing some small vault transformers for the distribution group because diagnostics was in substation piece of this thing and transmission. And that's the group I was in. So we periodically went and helped the distribution folks out. We'd run some diagnostic testing. We'd test their underground switchgear in the downtown areas. We'd test some of the smaller vault transformers. There's a variety of things that we would do for them. Test the bus work, and we'll a little later we'll get into that. You understand why the value of that. And it was about 2 o'clock in the morning, and I was up in the van, and I was running this test. And I'll have to edit this part of the recording because, like I said, it's a secret. So anyway, as I'm running this test, this gentleman walks up that I'd never seen before. He's in a three-piece suit. He's all dressed up. It's 2 a.m. in the morning. I'm out there with my shirt tail out and my jeans, and I'm sitting in the truck. And we have a communication system on the high voltage lead, so there's a speaker on that lead that the line's constantly open for communication back and forth to the individual in the vehicle. And then that high voltage lead might be about, I can't remember how long they were. I think mine was like 70 or 75 feet. It was quite lengthy. I think we may have even on occasion had a longer one. But the other person on the end making all the connections, they'd be down in this vault. So you couldn't really even holler at them and they could hear you. So you just had this speaker on this thing. So I was up there. My other guy was down there in the vault. He was making all the connections. I'm up in the truck filling the paperwork out. This was back before we had computerized test sets. This guy in a three-piece suit walks up and he goes, "Hey, what are you doing?" And I thought, well, he looked kind of harmless. So 2 o'clock in the morning, downtown, you you wonder about those things. That's a really good time to get yourself into trouble. So he said, I said, well, I'm just doing some diagnostic testing for at the bottom of this building down here. If you've ever seen that big green building in Dallas, the one with the lights on it, that's where we were at. And I forget who owned it at the time. It might have been Bank One or somebody like that. So anyway, he said, yeah. He goes, what exactly is that? And I said, well, we're just checking the electrical insulation, the integrity of that insulation. And I thought that was going to satisfy this guy. And I'm still filling my paperwork out. And he goes, yeah, well, what kind of test is it exactly? And I said, well, it's a power factor test. Well, I thought that'd scare him off, right? And he'd just go, well, God, power factor. How do you spell that, you know? Well, that didn't happen. He kept quizzing me. It was that night, folks, that I realized how little I knew about what I was doing. Now, if you've never been there in your life, with any aspect of your life, then I'm not sure you're a human being. That happens to all of us. So maybe not on this topic, but on some topic where you think you know something about it until somebody really quizzes you about it. So if you report to anybody at a utility, if you're reporting to someone, you found yourself in that position before because they'd quiz you till you didn't know the answer. So I went back again and I said, well, you know, it applies a voltage, and we measure current, we measure watts, and I thought maybe that would scare him. It didn't scare him off, folks. So anyway, he said, well, you know, okay. He said, at that point, I think that it just dawned on me that I had no clue. I knew what numbers I was supposed to get, but I didn't really understand exactly what I was doing. This guy finally said he realized I didn't know what I was doing too. So he said, well, thank you. And he turned around and walked off. He was a very nice gentleman. A few minutes later, the distribution group came around the corner and they said, hey, Cox. He said, did you see the president of this bank down? He's down here. And I said, there's a well-dressed guy in a suit and everything. They go, yeah, that's him. I said, yeah, he was over here talking to me, asking some questions. And they said, I said, why? And they said, well, he used to be the director of engineering for Dallas Power and Light. So if that made you laugh just now, it makes me laugh now, but it didn't make me laugh back then. Very kind individual. So he went from being the engineering director at Dallas Power and Light to somehow ending up in the banking business. And this guy was the president of the bank. So that night when I went back to the shop, I grabbed every book that Doble made, ever produced, and I took it home. And I started reading. And I think I read for a year. So I just wanted to understand it, and then I wanted to be able to present it in a fashion that I thought would make sense to folks. So there's the formula. You can study this angle all you want to study it at some point in the future, and we'll give you a copy of the presentation. But bottom line, it's a power factor is simply a ratio of the power of what you measure in watts versus a calculation that you're going to make with your measured current and applied potential. So power factor is simply a ratio, and it goes from 0 to 100%. Or it goes from 0 to 1. So it's either 0 to 1, which we refer to as unity, and everybody hears about. If you're working at a utility, you've probably heard the term unity. You may even know what unity is, but it's current voltage being in phase, and that's how we like to deliver power to people's house. Because if I used to have a couple of power factor meters, I think my brother's got them now, and I don't know that I'll ever see them again, because my brother owns a contracting company, electrical contracting company, and he loves these meters. So one time I was at a house we used to live in. I bought a single-phase power factor meter from, I forget where, somewhere off the internet. And I hooked it up to my service at my house. I turned my air conditioner off because that was really the primary load in the house. And I measured the power factor coming in from what was then Encore. And it was about 99.9. It was very close to 99.9%. I was very, very, very close to unity. And so I went and flipped my air conditioner on, and it dropped down to 92%. And I thought, well, that's not bad power factor, right? The power company wants to get that current and voltage in phase to our homes, right, and to our businesses, because anything that's lost along the way, they're not making money on that, So it's like delivering. It's like you going out and buying a Coke and you pop the can open. There's only half of it in there. You're losing money. So you're losing value. So kind of think of it in those terms. Anyway, I checked it. And it was like 92%. Well, I went out and there's a guy out of Florida years ago that had put some power factor optimization, let's call it that, equipment as a small box, and I put it on the service, connected it up to the main bus, and every time an air conditioner came on, my power factor went back up to about 99.8. So it made my air conditioner tremendously more efficient from that standpoint, and as a result of that, I'm not paying for power I'm not using, right, that I'm wasting. So the idea is to make things as optimal as possible. We do it at the utility, and a lot of folks do it on their businesses, adding high-end capacitors to their chillers, their air conditioners, whatever it may happen to be, to try to make the power as clean and great as possible. So it's typically discussed in terms of 100% or 1.0 unity, those kinds of terms. But unlike the answer I got when I begged the question that day about what power factor is, and somebody said, well, it's not the same power factor. Power factor is power factor. It doesn't matter whether you're testing something, a piece of substation equipment, or whether you're talking about power quality, it's still power factor. So we'll just clear the air with that. Where unity exists, current and voltage are in phase. Okay? And that's kind of what it looks like. It looks a little better than that, but that's just me freehanding in PowerPoint. And I don't know that I'm that good at it. So the current and voltage are in phase when power factor is at unity. Substation testing measurements from a power factor standpoint, they're capacitive. And we'll get into that a little bit. Where capacitors are concerned, the current and voltage are out of phase by 90 degrees. Okay? And one reason is because we don't want power moving across that circuit. You think about that for a moment. Capacitors ought to be very close to a zero power factor. Now, we can't get there because there's no perfect capacitor, but we get pretty dadgum close to a zero. So the scale we're going to talk about is, again, and I think we put this up a few weeks ago, most of the time it's discussed in milliamps when you talk about your measurements in the substation, and we'll get into why that is in a minute. But if you converted 100 milliamps to amps, it's just 0.1 amps. So these are small currents, microamps, again, 0.001 amps, pretty low amps when you think about it. Nano, pico, you get the idea. They all speak to amps, these measurements of milli, micro, nano, pico, and so on and so forth. There's more to the scale, but I can't remember all of them. We use pico a lot for capacitance. Picofarads, right? So as opposed to a farad. So you convert that, you take it down, what is it, nine zeros. They all speak to amps, ohms, watts, volts, but for our purposes here, we're going to talk about it from the standpoint of amps. So I just put up a typical calculation, and we're going to call this a bushing because for some reason I can basically remember what charging current or loss current we measured on bushings. Not all of them, but if you took a 138 kV oil-filled bushing in a transformer, you might be somewhere in this general vicinity, 1.76 milliamps or 1,760 microamps. But you have to convert that to amps in order to calculate the power factor across that capacitor, and we'll talk about that capacitor in a moment. You apply 10 kV test potential, provided it's rated for it. The equipment's rated for it, and most substation equipment is. And then you actually make a measurement of the power across that circuit, and in this case it's 0.05. All bushings are not like this. I just pulled this out of my memory bank. So to calculate that power factor, you take your amps and your volts, and so that you can come up with your VA. 17.6 is the VA. You divide that into your measured watts across that circuit. And that's what the power factor guys do, the diagnostic guys. They come up with 0.05 watts, right? So that comes up to 0.0028, which is what the power factor is. So think about unity at 1.0. You're nowhere near that. You're not even at 0.1. So you're at 0.0028. Well, for most of us at the utility, I think probably I could say all of us at the utility that deal with power factor testing, this is all percent. So that puts that bushing at about 0.28%, which anybody in their right mind would say that's a good power factor on 138 kV bushing. So if you think for a moment about, because we perform power factor on capacitors, and there's a reason for that, and I'll get into it a little more in the next slide. But if you think about it, that's kind of how we move power. So how do you get, once you've generated power, and you're going to, let's say, you transformer main to get it out of a power plant, you can't have the conductor touching anything. If you do, you're not going to generate anything. So you have to move that power. There has to be an infrastructure, a highway to actually do that. So how do we do it? It's how we move power. Well, we do it with capacitors. So if you think about it, if you've ever seen bus work, right, coming out, what's it got on it? It's got insulators. And what are the insulators tied to? Earth. What is that? It's a conductor, an insulator, and a conductor. Isn't that a capacitor? So if you think about it, and I just, I just put some examples in here of the fact that bus work is supported by insulators, which are tied to earth, which make them capacitors. Typically not in the same function that we think of capacitors, but it's, bottom line, that's what it is. That's how you get power out. If you did not have that separation, you wouldn't be able to move power. So basic power factor testing. So we'll talk about bushings just for a moment to give the example. So the bushing has center conductor, insulator, many conductors and insulators actually, and we'll look at that. And another conductor in the form of a ground flange where it goes through the transformer. So isn't that what we have to do, right? We want to make sure that that energized conductor gets through that tank of that transformer safely without any distractions whatsoever. All right. So I call bad insulation a distraction because ultimately it's not good. So bottom line, there's a bushing, right? They're full of capacitors. That's what they're full of. So I'm going to turn this little pointer on in case you got a little glare on your computer. It's got a bunch of layers of insulation and conductor. So you have your center conductor, then you have paper wrapped around it, and then you have another smaller, different type of conductor wrapped around it with paper wrapped around it with that wrapped around again. You get all these capacitors, okay? So where this bushing goes through the transformer at the ground flange right here and bolts on and connects to that transformer, then you have this insulator, this outside, mostly porcelain insulator, let's say. Then you have your conductor coming in here up at the top. So you're trying to keep current and voltage on that conductor in phase as it goes through this bushing and out the other side. So that's true for all of the equipment. Circuit breakers, what do we use? We use bushings. Why do we use bushings? Because we can make these bushings with very, very good insulation so that the electricity, the current and the voltage have a safe path to the end user, right? So when I told you this was going to be a pretty simple look, I'm in it. So what do you do when you test a bushing? Well, you energize that center conductor. And then down here at the bottom, you have a return that you connect to a tap. And that allows you to measure that insulation and that capacitor. So in any kind of high or low voltage capacitor, you want a really, really good power factor, right? You want this thing to be close to zero because, again, you don't want the power getting diverted or distracted along the way. Because if power factor does that, you want it 90 degrees out of phase across that insulation. So that's why we do the testing. As opposed to being in phase across that capacitor, because if it's in phase across that capacitor, that's a bad thing. So it only makes sense that if the transformer's paper has been challenged from a dielectric perspective. So you have to think about it. Why do we do all those capacitors in that bushing? We're trying to obtain a particular dielectric that we want to see, so that the withstand across there, the insulation across there, can withstand X amount of kV, right? A good capacitor ought to be pretty close to zero. So when you look at it from this side perspective, you want the current and voltage out of phase by 90 degrees. Now, by the way, folks, there's a lot of other things that go into this, but remember, what we want to try to accomplish here is just a basic understanding of the principle. So you really want your current and voltage out of phase by 90 degrees, and as opposed to in phase across the capacitor. So when you think about a bushing, the ground flange, the tank is one conductor, right? Because the tank is grounded, and earth is a conductor. So you have your incoming conductor to your bushing. Your cable connects up, or your buswork to your bushing. So that connection remains all the way through, and along the way, you have this insulation so that the power has a highway to get through there. Okay. So not all that long ago, when we first started looking at the carbon oxide ratio for gases, we were looking at carbon monoxide and carbon dioxide, and Chris Rutledge over at Memphis, who is a very close friend of mine and still is to this very day, I'd first noticed this carbon oxide ratio and the fact that you could trend this ratio and find paper problems before hot metal gas started generating in a lot of cases, which I thought would make us a lot more accurate, and I think it has. So we've found a transformer late 2013, early 2014, and that he had there at Memphis. And one of the things that we noticed was originally back in 2010, before Chris ever before he was ever the assistant asset manager, the diagnostic crews had tested a transformer, and they had gotten on the low side capacitance here. Because if you think about it, you're tying each side together, so you're just making piece of copper out of that, a conductor. That's all you're doing. And all that insulation and that winding and that oil between there and the tank. It's a conductor, insulator, conductor, right? What do we call that again? A capacitor. So crews had tested this transformer back in 2010, and they'd had a 1.5% power factor, which is a bit high. But Chris noticed his carbon oxide ratio falling like a rock. And so in 2013, when we first found out about the carbon oxide ratio and trending that ratio, had the crews take his transformer out of service, and they tested this transformer again, because remember, no hot metal gas at this point had generated on this transformer. Therefore, the paper had not been thermally challenged. So you remember the example of taking the piece of paper up here and the cigarette lighter underneath it and kind of waving it back and forth. You begin to bake that paper. And when you bake that paper, it loses its absorption and dielectric capability. So now you don't have paper that is saturated in oil anymore. What you have is something very extremely solid that can't absorb the oil, which makes up a good portion of the dielectric between the turns of a winding. So if you haven't baked it yet, maybe there's an opportunity to correct the problem if you know what the problem is. And in this case, this transformer was soaking wet. Well, when they pulled it out of service to test this theory, they went out and tested it, and the low side went to 6.5% on the power factor. Okay, so when will it fail if you just left it and put it back in service? There's no real right answer to that question. It may fail the minute you put it back. It might fail in bridge after it reaches 2%. It might fail in bridge after it reaches 1.5%. In this case, obviously, it could go at least up to 6.5%, but I wouldn't expect it to live long in this condition. So knowing exactly how long, who knows? Nobody really knows the answer to that. But they took this transformer out of service, fixed all the leaks, repaired it, put everything back, pulled a vacuum on it, did a hot oil circulation on it, the whole 9 yards, dried that transformer out, got it back right, put it in service. Power factor came way down on this transformer. It's still in service today. So it got caught before it was thermally challenged, which was a great thing, because we know if the current and the voltage ends up coming into phase, so the closer to unity you head, and this is just in principle, you're bringing the current and voltage closer together. Well, what happens when they connect? Well, you're going to go boom, right? So we don't like boom. Boom's bad. So why do we do it? We've talked about that. No insulation is ideal, so you're going to have some amount of current flowing in the insulation, but the key is that it is very, very minimal. The leakage current actually is a resistive current and a capacitive current. In real life insulating conditions, the addition to the capacitance current, there will be a resistive or a loss current in phase with the voltage. Now, if that's more information than you wanted, well, that's okay. We've already talked about current and voltage and the relationship between the two as it relates to a capacitor versus the kind of quality of power we want delivered to our home, what ought to be actually on the conductor. So power factor is defined as the cosine of the phase angle between the voltage and the current. Ideal insulation, 90 degrees again, something we've already talked about. So most oil field bushings, high voltage and low voltage. Now, if you're on the call and you didn't know this before, and you now know, okay, well, that power factor across that capacitor needs to be pretty low. Well, now you know where this whole thing of 1% came from. So most of the time you test a transformer, given decent oil, larger transformer, let's say, particularly, you start getting into 2, 3, 4 MVA and up, that kind of thing. You're going to start seeing power factors that fall well below 1%. And for the bushings and for the windings as well. These are very, very good, tight, well-built insulation systems. So when they get challenged, they're, once again, they're communicating, right? So we probably mentioned this before. If I go to Japan and I try to communicate with most of the population there in English, there's a good chance nobody's going to know what I'm talking about. So that's why I think it's important to learn the language and be able to speak the language a little bit when you're talking substations. And so when you're talking to a diagnostic person that's performing this test, or, you know, it's good to have a little insight into that, because now maybe you might have a general idea of, maybe you never even thought about it before. That's my target audience this morning, somebody who might not have considered it. Or maybe there's some aspect of what we're talking about today that you can put in your arsenal. So when you talk about these high voltage capacitors and these low voltage capacitors that we have in substations in the form of bushings, in the form of windings on a transformer, when you short them together, you see them up there shorting the high side out. Well, why are they doing that? Well, they need to make one piece of copper there. And all the insulation that's associated with that piece of copper will be measured to earth. And they will look between those two conductors and calculate the power factor. Or these days, the test equipment will do it for you. You don't even need to know how to do it, which is why I think maybe this version ought to be communicated to everybody doing those kinds of things out in the substation. They'll at least have a basic understanding of it. High power factors. So, you know, if you have a significant change on a bushing, obviously you probably want to make a change or go ahead and replace the bushing. Now, I've told this to our internal folks on more than one occasion, and I'm running over a little bit. I'll take a couple of minutes here, and then we'll look at questions if there are any. There's a lot of risk with managing substation assets. So I've talked a lot about this internally with GE to our folks. Because sometimes people go, well, this is bad. Why didn't somebody replace it? Well, if you got an outage window of, let's say, 8 hours, and that's all you've got, every clearance is dependent upon, somebody's waiting on that equipment to come back for that next clearance to come in for that planner. And I don't think a lot of times maybe we as vendors, we might not quite understand that aspect of what you deal with. So when you turn in equipment to get an outage, you get your outage, but your outage being returned to service is what is dependent upon the next project that's going to happen. So when the planners give that outage window, they expect it to be back because most of the time there's somebody right behind you that they need that thing out for, need it back in service for, in order to get another circuit out. So from that standpoint, you may find a bad bushing. You may not have time to replace that bushing that day. And you desperately want to, but a lot of times there's things that will force you to not be able. You can't extend an outage maybe. So everybody talks about it and they go, okay, well, where were we? We're at 1.1%. We were at 0.6 before. We'll schedule to get this back out tomorrow and replace this bushing, or the next day, or whenever the planners will give it to you. You don't want to do that. And there's times when they'll let you push the outage and replace the bushing. And there's also assets out there you're not rolling the dice on. And those $1 million plus assets you don't really want to roll the dice on. So I've been involved in these discussions on multiple occasions where you're sitting around at a table going, look, if we don't do this, we run the risk of this. So there's a lot of back and forth that goes into these decisions about when to respond to these results. So probably if you're not involved in those conversations, hopefully that helped you gain a little perspective into what the operations folks deal with on a daily basis. So as a diagnostic guy, I used to leave a substation many, many years ago, and I would be disappointed if I didn't find something wrong. That's what I was there to do. I was kind of happy that everything was good, but I was also a little disappointed I didn't find something wrong because that was my job. I was supposed to be looking for a problem. We found our share of them too, by the way. So every once in a while, I remember the maintenance crews would not want to see us coming, right? Especially on a Friday afternoon. High winding power factor ought to be investigated. You just saw a good example of that. Those power factor readings don't go up for no reason. They go up for a reason. And as they increase, it's not good. Remember, we're trying to achieve pretty much zero in a capacitor, not unity. So if we're moving towards unity for any reason whatsoever, that's a bad thing. Never assume it's an acronym. Okay? So if you don't understand that, feel free to email me. I'll be more than happy to explain this acronym to you. Okay? So let's get to what questions we got, if anybody's got any. This is not the way you would probably talk about power factor if you were designing something. But if you're talking to folks that actually perform this test in a substation and you want to be able to communicate that in terms of a basic concept of why we do power factor testing, this is a great way to, at least in my mind it is. It's pretty easy to see that relationship between current and voltage, right? And understand that relationship and why you can't get power from one location to the other without actually performing power factor. Without actually employing a capacitive, in theory, capacitive highway for that power to move. So you can't. You see it in switchgear, in the buswork in switchgear between those separators. They're all those separators. You'll see micarta board there maybe. But the outside of that frame is conductive. There's your insulator and there's your conductor, and now you've already running a conductor through it. What does that make it? Conductor, insulator, conductor, capacitor. Some of these capacitors are really, really good, and some of these capacitors maybe not quite so good. So bushing's the same thing. Again, the highway of moving things down a line. What do you see on a transmission tower? you see it kind of hit a dead end, and it's jumpered, and there's insulators there, and then what? It's where are the insulators tied to? You know, they're tied to the tower. Where's the tower tied? To Earth. What does that make it? A conductor. So you have your conductor running down the line. You have insulators. You got an insulator. You've got a tower, which is grounded. What do you have? Conductor, insulator, conductor. You have a capacitor. So I try to think of things in those terms because most of us are managing and dealing with 100 things a day, especially if you're at a utility. You don't just have one job. I'd like to meet that person. You know, if you ever run into anybody at a utility that's just got one thing to do, call me up and tell me who it is, because when they retire, I'm going to work there. Normally, it's 100 things in a day's time that somebody's doing and dealing with, and they have to know all facets of everything. They got to have some general idea. If you're going to manage operations, you have to know a little bit, at least, about P&C. You have to know something about maintenance. You have to know something about the equipment. You have to know something about diagnostics. But you have to know, do you have to know everything about all that? No, you don't. Do you need to know something about it? Yes, you do. It's pretty important to know those things. So I just want to bring that up. Do find the same comparison trending of power factor capacitance for online monitoring as you find with offline tests? And does the 1% still hold true for the online monitoring? That's a really good question. So for online monitoring, you're measuring capacitance, the difference in the delta in the capacitance between the bushings. And so from that standpoint, you're not really calculating a power factor as such. So it's a different form of monitoring. So if you think about bushings and the layers of the insulation in the bushing, that as anything changes with those layers, you're going to change the capacitance. So the one thing you kind of count on is, which tends to work very, very well, is that all three bushings aren't bad when you connect your monitoring up, right? So I've seen cases where people have gone out to perform an offline power factor, for example, and they test all the high side bushings test bad. I probably don't believe that. I've never seen all three of them test bad, unless the transformer had caught on fire and burned them all up. Then they were all three bad, okay, on the high side. But so those bushings are you never really have more than about one of them go bad at a time, and those are kind of some of the things you count on. So when you connect up the bushing monitor itself, those capacitive measurements that it makes, and compares those and looks for the differences in those currents. I hope this was helpful. I know that it helped me tremendously when I first began to get involved in power factor testing. And when I had my moment in time back in my early career, so to speak. But I think a lot of this has, if you know something very, very well, it always behooves us, I guess is a good word to use, to try to take that knowledge and find a way to project the concept of that in a simple fashion. I like putting puzzles together. Not big ones, the ones that have about 3 or 4 pieces to them. Because I found that those are the kinds of things most folks can latch onto and feel good about, and walk away with some insight they didn't have before, and they tend not to forget if those kinds of presentations, let's say. Okay. Well, all right, everybody. Well, I appreciate you joining the call, and I hope everyone has a good, safe time together. And don't forget, don't tell anybody about that story I told you early on, okay? All right, everybody have a good one. Thank you for your time. Very much appreciated.